So, I'm assuming if you graphed this, you did an XY chart. Who can tell me what this looks like? Good start to the day. Excellent start to the day. Well, would somebody like to draw it on here? With coordinates and stuff. Ooh, Taryn, do you want to do it? I see so many fingers pointing at you, so I'm thinking that you do. Wow. All right, we don't have to freak out. Who wants to draw this?
Somebody will tell me how I'll draw it.
Come on, people. First day of class, we said something you can use all year to graph is an XY chart. An XY chart. Now, obviously, you can't plug in 0 into here, so I'm going to make my XY chart with -1 and +1, -2 and +2, -3 and +3, and we'll see where that takes us. Okay, plug in -1. That's 1 over 1, which is 1. Same thing for +1. Plug in -2. That's 1 over 4. Plug in +2, you get same thing. -3, same thing. 3, same thing. So if you plot those, that's 1, 1, 2, 1/4, 3, 1/9. And the same thing over here. Well, what if we try smaller numbers, like 1/2? We can see it's going to be symmetrical, so I'll just do the positive. And 1/3. You plug 1/2 into this, that's 1 over 1/2 squared, which is 1/4. 1 divided by 1/4 is the same as 1 times 4 over 1, so that would be 4. And by that same logic, you can go ahead and assume that that was 9. So, 1/2 4, 1/3 9. It's going to look the same over here. All right, now I'm going to have to set this down to accurately connect these dots. This graph, if you did it correctly, should have looked like a volcano shooting up towards the heavens. Like that. That's what that should have looked like. XY chart. Before we go any further, are there any questions about why it looks like that? Okay. Normally, when you can't have a 0 in the denominator, remember we talked about that when we talked about domains of a function. When you can't have a 0 in the denominator, most of the time that's going to generate a vertical asymptote. Asymptote. A-S-Y-M-P tote. So whatever values aren't in your domain, most of the time, I'll show you the exceptions here in a minute, wherever that happens, so in this case just 0, there's going to be an imaginary line, a vertical line at that exact spot, where your graph will not touch but will ride right along next to. So for this one, that was the line x equals 0. An imaginary line that your graph is going to get closer and closer to from both sides but not actually touch. That is a vertical asymptote. Our whole lesson today is about asymptotes, vertical asymptotes, horizontal asymptotes, even slant asymptotes. That's what we're doing. We're going to graph these and then move our graphs around said asymptotes. And when we do this, we're going to be primarily looking at 2 functions, although to start out we won't, but 2 more parent functions you might want to add into your notes. 1 over x squared, which will always be just kind of a volcano. But this is going to have the same kind of shift as all of our other ones did. For instance, if I had said 1 over x minus 2 squared plus 3, it's still going to shift right 2 up 3, just like all the other ones did. So this would come right 2 up 3, and your volcano would be centered around this spot instead of the origin. Thanks, sir. Yes, the parent function, you might want to quick sketch it. It's going to work just like our others in terms of shifting. And the other parent function you need to add into your notes is 1 over x. 1 over x, well, I'll just sketch it real quick. If these are my axes, this is just an absolute quick sketch. 1 over x, you can do an xy chart and get it more accurate. It's going to look, oh, that's not right. It's going to look something like a dece. It's going to look almost the exact same as 1 over x squared, except this piece is going to be down here because it's negative. Whereas x squared, the squared made it a positive and therefore made it above the x-axis. On 1 over x, it'll be below. Now that's a very rough sketch, but that's the general shape of it. And you can plug in points for x and y and get more accurate coordinates, but that's the general shape. So 1 over x squared. Parents that we are looking at today. Although we're not going to come back to these for a few slides, we're going to first focus on general asymptotes, and we'll come back to those two parents. All right, next slide. First kind of asymptotes we're going to look at, never mind, we're doing domain. I guess they're going to try to refresh us with these vertical asymptotes. What cannot be in the domain for number 1? 4. That's right, the number that can't be in the denominator. What about number 3? 5 and negative 4. What about number 5? Now, quick little thing here when it comes to asymptotes, which technically we haven't started yet. You're correct. 7 and negative 7 won't be in the domain because even though x plus 7, if you were to factor, is going to cancel at the top, that doesn't change the fact the original function had an x plus 7, x minus 7. Let me just go ahead and jump into the meat of today. Wherever this happens, you're going to have a vertical asymptote. So I would immediately on this one go to x equals 4, make myself a vertical asymptote. On these two, I'd go to positive 5, negative 4, and I'd have 2 vertical asymptotes. On number 5, even though 7 and negative 7 can't be in the domain because of the original, because the x plus 7 cancels, there will not be a vertical asymptote at negative 7 because it's no longer going to affect your function. There would only be one vertical asymptote at positive 7. So that's the one place where the domain and the vertical asymptotes diverge. And number 7, any vertical asymptotes? No, nothing's going to make that negative. All right, let's... Vertical asymptotes. Oh, we're just going to start with both of them. On this function, there are 2 vertical asymptotes here and a horizontal asymptote here. Notice how our functions kind of gravitate towards them and ride right along next to them. Classic vertical asymptote stuff. So, these are saying, as x approaches negative 3 from the left-hand side, so here's negative 3. As I approach negative 3 from the left, where's my function shooting off to in terms of y? Negative infinity is how you'll answer that. You're correct down, but you'd actually answer it negative infinity. When you have a vertical asymptote, it's always going to shoot off to positive or negative infinity at one of those asymptotes. What about positive 1 from the left-hand side? That little minus means from the left. A little plus sign would mean from the right. Positive 1 from the left-hand side, where's it going? Negative infinity again. They didn't give us any positives on this slide, but an example of a positive would have been like positive 1 from the right-hand side would have been positive infinity. Whenever x asks you for, as x goes to infinity, that basically means as x shoots off to the left, because it's negative infinity, what is my graph tailing off at? And that'll pretty much always be the horizontal asymptote. So where does this thing look like it's getting closer and closer to? In terms of, 0. Getting closer and closer to 0, which was our horizontal asymptote. Any questions on where any of those 3 answers came from? All right, let's look at a few more. All right, same kind of thing. I'm going to give you a second to look at it yourself, and then I'll call on people to answer. Take a second to look those over. I will call on somebody at random to answer. Josh, while you're looking at that, give me a 2-digit number. 1, 2. First row, second row. Keith, what about number 15? Let's see. Positive 1 from the right-hand side. Positive infinity. Very good. 2-digit numbers. Any 2-digit number. 47. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. Holly. Number 17. Negative 2 from the right-hand side. Where's that going? Very good. A lot of people tend to just look at the asymptote and say, oh, infinity. But you have to find the actual function. And the actual function is going down to negative infinity. Very good. 2-digit number? 32. That's you. Number 19. Where's the graph leveling off at as it shoots off to positive infinity? What y value is that? Very good. Very good. It's tailing off. Now, you might see, your function should never cross a vertical asymptote, but a horizontal one they may cross, but it's still going to level off there. And that answer is 1. Very good. Questions about any of those 3 responses? Any of those 3 answers that you're a little curious about where those came from? Okay. Next slide. Find the vertical asymptotes. Same thing as the domain. All you're telling me is where they exist. Number 21. At what x value, or excuse me. Well, no, that's right. At what x value am I going to have a vertical asymptote? Very good. So x 21 would be x equals negative 4. That is the line that forms your vertical asymptote. What about 23? What 2 x values are going to make that thing 0 in the bottom? 0 and negative 4. Very good. 25 is a tad trickier. Very good, Joey. Why not 0? That's right. It would just factor out. Technically, it can't be in the domain, but it's not going to affect your graph once it cancels. Very good. And 27, vertical asymptote. There isn't one. Just like the domain. You can't square any real number and get negative 4, therefore making that 0. So that one won't have a vertical asymptote. Not going to have one. Questions? Because there's nothing the denominator cannot be. There's nothing you can plug in that's going to give you a 0 in the denominator. If you plug in 2, that's just going to be 8. Etc. Any other questions? All right. I don't know what that was. Horizontal asymptotes. Okay, you need to make a little bitty chart in your notes. There's a horizontal asymptote chart. Horizontal asymptote chart. We'll call it the hack chart. There's only 3 possibilities for horizontal asymptotes. Only 3. And those 3 possibilities are solely determined on where is the highest power. Highest power location is the only thing that matters when it comes to horizontal asymptotes. So we're going to find that highest power, and that will determine what our actual horizontal asymptote is. Those are the only 2 columns in this chart. The 3 possibilities are this. The highest power lieth in the numerator, it lieth in the denominator, or they are the same. They have the same highest power in both the numerator and denominator. Now, horizontal asymptotes are basically nothing more than as your graph goes to positive and negative infinity, as you plug in ginormous x values and negative ginormous x values. Now, that's important because the highest power, as your x's get bigger and bigger and bigger, as you punch in 100,000 and a million and a billion in for x, eventually your highest exponent is going to dwarf everything else in the function. It doesn't matter if your polynomial is 7x to the 7th, 6x to the 6th, something x to the 5th, 4th, 3rd, 2nd. Eventually, that 7th power, that highest power, is going to just dwarf everything else. That's why that's the only thing that matters when it comes to horizontal asymptotes. Now, if it's in the numerator, if your horizontal asymptote is in the numerator, then that means your numbers are just going to keep getting bigger and bigger and bigger, right? Because you'll have like 1,000,000,000/5. Well, that's just a really big number. So, if your highest value is in the numerator, then you aren't going to have a horizontal asymptote. None. You won't have one. Because it's not going to level off anywhere. It's just going to shoot upwards or shoot downwards. It's going to shoot up or shoot down. And in those cases, you're going to have standard in behavior like we've already done before. When it's in the denominator, let's say you have 4x cubed on the top and 7x to the fifth on the bottom. If you punch in 1,000,000,000 for x, you're going to get like a big number and a ginormous number on the bottom, which would probably reduce to something like 1/1,000. 1/1,000 is a small decimal. And the smaller your decimals get, the faster they approach what number? 0. If your highest power is in the denominator, your horizontal asymptote will be y equals 0. Right there along the x-axis. And I'll quick sketch that over here. What that would mean is, any function, think about it, 1/x and 1/x squared, the two parents we did today. Classic examples. The only variable, therefore the highest variable, was in the denominator, and both of them tailed off along the x-axis. Whether it was above or below for the moment is irrelevant. They both just tailed off along that x-axis. If they're the same, if you have the same highest power in both the top and the bottom, then they're going to just keep getting bigger together at the same rate. And the only numbers that are going to matter, it doesn't matter how long your polynomials are in the top and the bottom, as the only thing that's going to matter in the end is still that highest power, so you can cover up everything else and reduce. 31, what would that reduce to? 4. And that would be your horizontal asymptote. Y equals 4. So, I'm going to put, when they're the same, you just divide the leading coefficients. Leading coefficients. Assuming they're already in descending order. And that's all there is to those. 12/3, 4. What other problem on the board is going to have a similar horizontal asymptote situation where you have the same exponent in the top and the bottom? 35. And what's it going to be? -2/3. Only thing that matters. So this one would be y equals 4. Y equals -2/3. Unlike vertical, where you can have any number of vertical asymptotes, you'll only ever have one horizontal asymptote. Only one, or none. Questions about those? We've done vertical, we've done horizontal. And we've got 2 slides left. Alright. Okay, now, remember I said we were coming back to these. If you know what the parent looks like, then you know what these look like, because it's going to shift the exact same way. Where's this thing shifting? Right 1. There's a -1 inside the function, so you'd have your 1/x function, which you've already drawn. In fact, you're actually going to sketch these, but they don't have to be perfect. Think about it like this. Now, they want you to think of it in terms of asymptotes. Okay, let's think of this in terms of asymptotes. Where does this thing have a vertical asymptote? Where's it going to have a horizontal asymptote? Where's the highest power? It's in the bottom, therefore your horizontal asymptote is 0. So if you just sketched those... Were you asking a question just now? Okay. If you were to sketch this graph using those asymptotes... Diagram it. Hold on. So, here's what that would look like. I'm not going to do this for all of them, but this is how they'll all work. So, my asymptotes were x equals +1, so right about there, and y equals 0, because it had a horizontal asymptote of 0. So you just sketch your parent graph around your new asymptotes. The parent was 1 over x, which was like this. Oh, dang it, I do that every time. That was the 1 over x. Granted, it wasn't supposed to cross. So ours would look like this. You can just sketch them. And you notice that's the exact same thing as the parent, just shifted right 1. What about 39? Where's that thing shifting? Up 2. So this portion would just be here. 1 over x shifted up 2 units because your horizontal asymptote would shift up 2. What about number 41? Somebody other than Drake. Where's 41 shifting? Left 1 and down 2. So our asymptotes, which would start here, would shift left 1, down 2, and you would sketch it around those asymptotes. Same exact thing for 43 through 47, except instead of looking like this, it'll look like 1 over x squared, which was our volcano graph from the DOM. That's all there is to those. Shifting your asymptotes. Questions about those, about what you're going to be asked to do? You just sketch them. They don't have to be perfect. Notice, they didn't bother giving you like a 3 or something in the numerator. If you remember, back when we did all these shifts, we also like multiplied by numbers. Those are really hard to see in 1 over x squared. Like 1 over x looks like something like that, and like 3 over x has a slightly different bend, but it's so hard to see that I'm not worried about it. If you want to get precise, you can always plug in values. That's why they didn't even bother. Now, I don't see one of these like this up here, but let's take a look at this one. What if this had been a negative out in front? How would that flip it, you think? Dang it, I just answered my own question. Darn. It would just flip it. If you had a negative, it's going to flip it. Negative over here, it would just flip it. Same thing it did with all these that are hung on the wall. Although that may not even come into play today. Last thing we're going to look at are slant asymptotes. You might have an asymptote along a diagonal that your function is going to ride along next to. You will only have a slant asymptote if the numerator is exactly 1 power higher than the denominator, you'll have a slant. If it's not, you won't. Notice, 1 higher, 1 higher, 1 higher, 1 higher. When that happens, you'll have a slant. When it doesn't, you won't. Yes. Okay. Highest. The highest. So, to find those, you just do division. You can either do long division, or looks like on 75, you can do synthetic division. Although I look at 71 and 73 and wonder if you can't do synthetic with a 0. Never tried. I bet you could. But I'm not going to say you can because I've never tried it, but I bet you could. But you just divide, either using long division or synthetic division. Whatever's left is your slant asymptote. Let's look at one. Oh, then they want you to graph them. Well, you don't have to graph them. I'll show you what a graph looks like. Let's see. Looks like 77 would probably be the hardest one. So we're dividing. I know you guys loved this section, so you should really enjoy this. The beauty of this is you don't have to worry about the remainder when it comes for slant asymptotes. If you have a remainder, you can just chuck it, because it's not going to affect your asymptote at all. All right. X cubed divided by x squared. X, multiply it back through. X cubed plus 2x squared minus, that's negative 2x squared. Divide it again. Negative 2x squared divided by x squared minus 2. Now, even if we have something left, it'll just be a remainder, won't it? Chuck the remainder. Here's your slant asymptote. It'll be the equation y equals x minus 2. And here's what that would look like. I'm going to quick sketch this function. Oh, dang it. Let me get some axes on here. Here's what that would look like. For the asymptote, for that slant. Oh, are there any other asymptotes for 77? Well, let's see. You can't just assume that. You have to solve it. Factor out an x. What's going to make that thing equal to 0? 0 and negative 2. So, you're going to have vertical asymptotes at 0. Wow, that's really bad. I thought I was on my line drawer thingy. There we go. You're going to have vertical asymptotes at 0, negative 2, and you're going to have a slant asymptote on the equation x minus 2, which is just a line with a y-intercept of negative 2, looking about like that. Looking about like that. Now, only question now is, when you start graphing this thing, I am going to actually probably give you one today to graph, just to see if you can put it all together. So here's all my asymptotes. You'll never have both a slant and a vertical. And a horizontal, by the way, which is obvious because for you to have a slant, the 1 pi power higher, it falls into that situation of no vertical asymptote or horizontal because your highest power is on top. Okay, so you know it's either going to look like this or this on here. It's either going to be an upward parabola or a downward parabola in the middle. You just don't know which side of the asymptotes they lie on. So all you have to do is punch in a value around those vertical asymptotes, and you can assume the rest. Okay, so let's say I'm going to punch in. Ooh, that looks funny. Whole line. I'm going to make myself an XY chart. I'll punch in a number to the left of my vertical asymptote, like negative 3, a number to the right, like negative 1, and a number to the right of my last vertical asymptote, like positive 1. Believe it or not, that's all you need. Because the definition of an asymptote is that it rides along next to it, so you just need to know which side of it it's on. If I punch in negative 3 into my function, let's see, it's going to give me negative 27 plus 1 is negative 26 over 9 minus 6, which is 3. So that's a negative number, right? So I come over to my graph. Well, I'll find them all first. I'll just find them all first. Plug in negative 1. You get 0 over anything is 0, so I can just 0. Plug in positive 1. 2 over 3. Now I'm going to plot these points, and I can just use those very few points to figure out where the rest of my graph is going to be. Negative 3, negative 8 1/3 will be down here somewhere, so it's going to be below that slant asymptote. 8 2/3. Negative 1, 0, and 1 comma 2/3, which is here-ish. So I can use that to make the following assumptions, because it's not going to cross my asymptotes. That means I'm going to come in and kind of bend down. I'm above the slant asymptote up here, so, well, I just did that to show you the continuation of the asymptote, but that was a mistake. Something like that. And I know it's going to be above over here. All you needed to know was whether it was above or below your asymptote. Well, this one actually might cross, I guess. I might want to put that in. One more value and just see. So that's the general shape of it. This one might have a little tweaking to do, but these two are good. You only have to graph one of these today, so just punch in enough points to where you feel comfortable with it. Yeah. And you're only going to be on one side of that. This one in the middle might be a little different, but for these two, it's just going to loop around the asymptote. And you're more than welcome to punch in your calculator and verify that by graphing this, but you should see around the same thing. Questions about where I got any of those asymptotes from? Okay, here is your assignment. 72 through 78. 6. I only want the slant asymptotes, but I want you to graph number 78 only. 72 through 76, all I need is the slant equation. But for 78, I actually want you to graph it.